Hi everyone, my name is Uri. I'm a research engineer from Yahoo, Tel Aviv, in Israel. And this talk is going to be a bit technical. So those who've never seen a line of Python, it might be a bit complicated. It might be a rough start. So, aspect-oriented programming for data science. Today, we are going to cover what is aspect-oriented programming, how do we implement aspect-oriented programming with decorators in Python, and then we'll finish off with 5 useful applications of decorators for those working in Jupyter. So, aspect-oriented programming isn't a new thing. It's a concept for minimizing cross-cutting concerns. Cross-cutting concerns are things that are hard to encapsulate in one module that come over again and again all over the application. For example, logging is a classic one. Security, data validation, caching, those are the classic implementations of aspects. All major programming languages have some kind of support for aspect-oriented programming. In C#, those are called attributes. You can see here an example. I think it's from a word add-in. And in Java, you have annotations, and Aspect-J gives you full support for aspect-oriented programming. This talk will focus on Python. So, those who've seen those who played with Flask before know that this is a fully functioning web server that always returns hello world, but still fully functioning. And this magical @ sign with the app.route, this is your decorator. By the way, this sign in Hebrew is cutely called a strudel. So I think you'll be familiar with it. So what is a decorator? We can see it here, but what does it do? So if we go to the formal definition, it's kind of obscure. So a decorator is a function that gets another function as a parameter, does some magic with it, and then returns a new function. What is it? Why do I need it? So I always find that it's most easy to set an example than to formally define. So this is a simple decorator that gets any kind of function, and just before returning its value, it also prints it to the screen. So here we can see on the left-hand side, the decorator. We define a function called log_print that gets another function f. The green function is our new function. Here we define that we actually run the code and print it and then return it. And since after using this @ sign, this magic strudel, all we are running, in fact, is the green function and not the original function that we wrote. So here we can see this increment function that takes a number and increments it. After using the decorator, what I'm actually calling is the green function. So the value is getting incremented, but also printed to the screen. I hope that made things simpler. In Python, those who prefer the class object-oriented notation, the same code could be also implemented with the Python magics, so with the init and call. I personally prefer the functional programming syntax, but those are functionally the same. Okay, now it's time for the fun part. Okay, so for our first useful decorator, I will be presenting 5 decorators. Hopefully, at least one of them would be useful for you. So this decorator is a built-in, and what it does, it memorizes intermediate results in memory, and then instead of calling the function again, it pulls it out of the memory. So let's see, I guess that the Fibonacci function needs no introduction. So this is a rather naive implementation of it. And as you can see, it runs for approximately 403 milliseconds. And using the built-in LRU cache, LRU is less recently used cache with a maximum size of infinity. So it saves all the intermediate results and just pulls them out of memory if it can. Now, the runtime is actually 116 nanoseconds. So 116 nanoseconds in comparison to 403 milliseconds, just by adding like 10 characters. That's pretty impressive. But on the other hand, I don't know, I don't use the Fibonacci function like every day. But the Levenstein distance, on the other hand, is a bit more useful. Anyone who's done basically anything with natural language processing is at least heard about the Levenstein distance. Levenstein distance is between two words or two strings. It's basically the number of addition and deletions that I need to do. So, for example, if my origin word is the word reshape, and my target word is the word shapes, what I need to do in order to transform from one string to the other is to delete two characters, the R and the E, and append an S at the end. So those are two deletions, one insertion. In total, 3 changes. So the Levenstein distance would be 3. This is how you calculate the Levenstein distance in Python. Not super exciting. And in order to test our performance increase, I randomized 10 words out of the built-in dictionary that every Linux distribution has. As you can see, those words are pretty random. And I ran all possible combinations, so 10 times 10, 100 combinations, and averaged the time it took for all the functions. So first on the classic Levenstein function, and the second time on the LRU cached one. As you can see, on the first function, we got almost 40,000 milliseconds. And on the cached version, 10 milliseconds. Super impressive. Just typing 10 characters, and we got like, I think it was like 5 orders of magnitude, 4. So without any effort. However, you can't cache in memory everything. We do have limited machines. So the next logical step is to cache intermediate results into the hard disk. So this is a rather naive decorator. You don't need to memorize or anything the code, but the gist is that if the result exists in a file name, so if path is file whatever, then we pull it up to the hard disk. Otherwise, we actually call the function and save it to the hard disk. So believe me that it runs faster after the second time. But what we really want to do, and this is where a bit of Python needs to be used, we really want the file name to reflect the arguments of the function. So we would want to call something, the Fibonacci function, for example, on variable n, and have that value of n saved in the file name, so I would be able to better retrieve it. Now, this is where Python gets a bit complicated, because there are plenty of ways to define a function in Python. So those are the same function implemented 3 times. This function gets 3 numbers and sums them. And the third argument is optional and default 3. But we can define it in 3 different ways. The first one is by named arguments. I call them the arguments actually A, B, and C. The second time is by positional arguments. So I don't know how many arguments I would have, but the first 3 would be summed. And the last one is by using key value stores, key dictionaries, actually. Again, same functionality, but when I get this function as a parameter, I need to interact with it some way. So this is where the inspect module, the built-in inspect module, comes to hand. It's very handy. So the inspect module allows me to bind parameters into a function without caring how is the function defined. It could be either named, ordinal, I don't really care. So this is how you use the inspect module. I extract a signature, and then I bind my data. Using this trick, I can actually write a decorator that gets the arguments and passes them on to the format function. So every time you see a curly braces, like we saw before, over here, they are going to be replaced by the Python built-in function, built-in format function. The next thing that, that the inspect module allows me to do is to get a function and extract its source code. Now, this is useful in one particular scenario that I use like almost every day. And this is a decorator. I'm shamelessly promoting a Python package I developed called SSH Decorate. Feel free to look it up. What it does, once decorating a function, first we connect to an SSH server with my super secret credentials, user and password. All we need to do is to decorate a function with the name of the server, and then every time I call that function, it's actually being run on the remote server. Now, the remote server doesn't have to have anything installed. This package actually takes the function code, types it on a remote terminal as if a user was typing it, and yields me the code back. Very convenient, needs zero installation on unknown servers, and works like a charm. So this is a local call that runs the get current working dir on my local machine. And the same function, decorated, gives me the remote home directory on my server. Very useful, especially when connecting to a lot of different servers. Another nicety of this model is that you can run bash commands with a very unique syntax, which looks like a terminal. This has nothing to do with decorators, but it's fun. Our fourth useful decorator is regression tests. So a lot of time when working in data science, we work and develop an initial model, and then we optimize it. And we want to make sure that the results are the same, apart from performance. So a simple way is to do regression tests. In regression tests, we basically record our initial value on our less optimized function, and then test it against our optimized function. So again, to Fibonacci. This is the naive implementation of Fibonacci. I run it 4 times. And these are the test cases. And this is the code I carefully copied from Wikipedia of the Fibonacci formula. Okay, obviously it should run faster. And now I replay our test cases. And oops, the functions differ on n equals 0. Apparently, the initial value is different. So very easy, very simple, nothing too exciting. And the last decorator I want you to see is some kind of Jupyter magic. So I don't know if you got a chance to play with the built-in Jupyter functions, but they are really cool. And Jupyter allows you to implement interactive functions, which means, for example, this function calculates the square root of its parameter. Just by decorating it with the interact and the ranges, I can now play with it and get the result. It's very useful to impress your colleagues. Now, the same thing could be done with the matplotlib library. So this function plots a Gaussian, and I'm playing with its standard deviation. Super impressive. Okay, all of the code snippets you've seen, all of the libraries, all is freely available at my GitHub account over here. And thank you. I'll take any questions if you have any. Thank you.